Hello students, today I am going to discuss about the last topic of electrostatics, and that is capacitance. First of all, I will start with classification of materials, and they can be classified as conductors, insulators and dielectrics. On the basis of their conductivity, they can be classified as conductors, insulators or dielectrics. Now conductors are those which can conduct the electric charges. When they are given, when some charge is created inside them, their charge is free to move and it moves along the direction of the electric field. Now insulators are those in which the charges are not free to move. The third one are dielectrics, and they have a property in between the conductors and insulators. Means ordinarily they behave like insulators, but when they are placed inside an external electric field, they start behaving little bit like a conductor. So in this particular section we are going to discuss particularly about the dielectrics. Okay, now next is conductor inside a electric field. We will discuss that what happens when we place a conductor inside an electric field. Suppose we have an electric field in some region. The direction of the electric field is from the positive plate towards the negative plate, and if we place a conductor inside it, then the free charges that develop inside the conductor, they start moving. The positive charges start moving towards the negative terminal, and the negative charges that developed starts moving towards the positive terminal. Actually the negative charges accumulate, they are free to move and they can accumulate on the one end, and as a result, since negative charges from this end move towards this end, a equal positive charge develops on the other side. The actual phenomena is this one. So the negative charges comes here and the positive charges accumulate on the other side. So the electric lines of forces, they come like this, and this way. So you can see that outside the conductor there is electric field, but inside the conductor there is no electric field. So the properties of the conductor when it is placed inside the electric field are: the first property is there is no electric field inside the conductor. Second, since electric field is not there, so you can say that there is no net charge inside the conductor. Inside the conductor there is no charge. And third one is the electric lines of forces, or you can say simply the electric field at the surface of the conductor is perpendicular to the surface, is normal to the surface. So these are few important properties of a conductor when it is placed inside an electric field. Now we come to the main topic, and the main topic is capacitance. First is capacitance. And experimentally it is observed that when a charge is given to a body, it increases its potential. The charge on the body is directly proportional to the potential of the body. The reason is, suppose we have a body A, now we give some charge Q1 to this body. Now that charge can be easily given to this body as there is no charge already there. Now this body is charged with Q1, and now we want to bring the charge Q2. So now we will have to do some work against the electrostatic force of Q1. So it means that the work done per unit charge, or hence the potential of the work done per unit charge is increased, and hence the potential of A is increased. Now here we have Q1 plus Q2. If you want to bring Q3, now further you will have to increase the work. It means the potential of the body is further increased. So the charge on the body is directly proportional to the potential of the body, and this implies Q is equal to CV, where C is a constant of proportionality called as capacitance of the conductor. Capacitance of the conductor, and its value does not depend on the nature of material of the body, but depends on nature of the medium in which the body is placed. Means simply that it depends on the permittivity and dielectric constant. So this constant of proportionality is called as capacitance of the conductor. So it means C is equal to Q upon V. Now if I take V equals to 1 volt, then C becomes equal to Q. So from here we can define the capacitance as the charge. Capacitance is numerically equal to the charge which will raise the potential of the body by 1 volt. Capacitance of a conductor of a body is the capacitance of a body is numerically equal to the charge that will raise its potential by 1 volt. This is the definition of capacitance. SI unit is now C equals to Q upon V. So Coulomb per volt, which is also called as Farad. Denoted by capital F. The SI unit is Coulomb per volt, which is equivalent to Farad, and it is the symbol for Farad is capital F. Now we can define 1 Farad also. 1 Farad equals to 1 Coulomb upon 1 volt. So the definition of 1 Farad is the capacitance of a body is said to be 1 Farad if 1 Coulomb charge raises the potential of the body by 1 volt. If 1 Coulomb charge increases the potential by 1 volt, then whatever is the capacitance of the body is called as 1 Farad capacitance. This is the definition of 1 Farad capacitance. Now we have generally what happens is the capacitance of the bodies is very small. So the practical units are, it's the smaller units. Smaller units are the practical units, which are microfarad, which is equal to 10 raised to minus 6 farad, or double microfarad 10 raised to minus 12 farad, which is also called as 1 picofarad. So 1 picofarad or 1 double microfarad, it is 10 raised to minus 12 farad, and 1 microfarad is 10 raised to minus 6 farad. These are the practical units of capacitance. Okay, next is capacitance of an isolated sphere. Suppose we have an isolated sphere Isolated means separated, completely separate from its surroundings. We have an isolated sphere whose radius is r, and let us suppose that the charge at the center of the sphere is plus q. Then we want to find out the capacitance of this sphere. So let us suppose that at the point V is the potential. So V is equal to 1 upon 4 pi epsilon naught Q upon R, and therefore the capacitance is Q upon 1 upon 4 pi epsilon naught Q upon R, because C is equal to Q upon V. Yes. So Q is this much and V is this expression. So they will get cancelled and you get 4 pi epsilon naught into R. This is the capacitance of an isolated sphere. Now next topic is important topic. It is parallel plate capacitor. Next topic is the parallel plate capacitor. Now simply the capacitor is any device that can store the charge. Any device that can store the charge is called as a capacitor. Now this capacitor we have different types of capacitors, like suppose a spherical capacitor, cylindrical capacitor and parallel plate capacitor, depending on the shape of the plates of the capacitor. Now if the plates are spherical in shape, suppose we have one plate and this is second plate and this is your plate A and this is plate B, then this is called as a spherical capacitor. Now if suppose you have cylindrical plates, this is plate B, this is plate A and it is earthed here, then this is cylindrical capacitor. Parallel plate capacitor have parallel sheets as its plates and therefore it is called as a parallel plate capacitor. So it means that the capacitor have different types just on the basis of its shape of the plates. Otherwise their working is quite similar. Now in our syllabus we have this topic only, the parallel plate capacitor, so we will discuss about this parallel plate capacitor only. Okay, so let me start from the beginning. Suppose we have a plate, or simply you can take it like this. Suppose we have a plate A. Now when we give the charge to this plate, and this plate will go on accepting the charges, and as a result its potential will increase, and we can continue this process till the plate achieves its maximum potential. When the plate will reach the maximum potential, after that whatever charge you give to this plate will be leaked to the surroundings, and the charge on the plate A cannot be increased further. Now we place another plate. This is the ordinary capacitance of the plate A. Now we place another plate B at a small distance from A, and when we place it here, as a result the negative charges get accumulated on this side of the plate due to the attraction of these positive charges, and the positive charges accumulate on the other side. Now these positive charges, they will increase the positivity of this plate, and hence they are increasing the potential of this plate. Whereas these negative charges, they are decreasing the positivity of this plate, and hence they are decreasing the potential of this plate. Since these negative charges are closer to the plate A, Therefore, their effect will be more as compared to the positive charges on plate B, and hence overall there will be a decrease in potential. The potential will decrease from Vmax to a certain value. So now the potential of this system is not at the maximum value, so you can further add some charge, but though that charge will be very small, because this effect this can decrease this the effect of these negative charges will be very small, and they can only reduce the potential by a very small value. Now, so it means when we place we had a plate A with maximum potential and the maximum charge that can be stored on the plate A. Now when we place another plate B parallel to it and at a very small distance, we decreased the potential little bit, and now we can add further charge to A. As a result, it means that we have increased the capacitance of plate A by placing another plate B near it. Now we earth it. We earth the second plate. Now due to earthing, all these positive charges, they will flow to the ground because of the repulsion of these positive charges, whereas these negative charges will not go to the ground due to the attraction. So now there are no positive charges here. We have no positive charges here, and therefore the potential of this plate will decrease by a large amount, and hence now we can add a large amount of charge to this plate, and therefore we have increased the capacitance by a large amount. This is the working principle, this is the working of a parallel plate capacitor. So what we do in a parallel plate capacitor? We take a plate A, give some charge to this, it reaches the maximum potential, then we place another plate B parallel to it, it decreases the potential of A by a small amount, and then we can add a small amount of charge further, hence increase the capacitance by a small value. Then when we earth the second plate, all the positive charges go to the ground, and hence the potential of, now we have only the effect of negative charges, so the potential of this plate decreases by a very large value, and therefore we can give a large amount of charge further to this plate A. Thus the capacitance of plate A is increased by a large value. Now again, we can have different type of material, we can have different mediums between the plates here. Generally, if we have air in between the plates, we call that capacitor as air capacitor. Air capacitor. Okay. This is the working of a parallel plate capacitor. Now we will obtain the expression for the capacitance of a parallel plate capacitor. Expression. We have a plate A, we have another plate B separated by a distance D, and let us suppose that sigma is the surface charge density on plate and A is the area. Area equals to, area of the plates is equal to A. Now electric field between the plates is sigma upon epsilon naught. We have already derived this formula in Gauss theorem. So electric field between the plates is sigma upon epsilon naught. This implies E is equal to, now sigma is the surface charge density, so it is Q upon A. Suppose Q is the charge on the plate, so you can say Q upon A upon epsilon naught. So Q upon epsilon naught A. Now the potential difference V is equal to E into D. Now we have the potential difference, E into R is the potential difference. So potential difference between the plates is electric field between the plates multiplied by the gap between the plates, which is equal to D. Now E is equal to this value, so QD upon epsilon naught A. This is our V value. Now capacitance is equal to Q upon it is V. Q upon V is capacitance. So this is Q upon V is QD upon epsilon naught A. Q and Q will get cancelled, epsilon naught A upon D. So the capacitance C is equal to epsilon naught A upon D. This is the expression for capacitance of a parallel plate capacitor particularly. Now, if suppose instead of air, we have some dielectric material with dielectric constant K in between the plates, then this capacitance will become K times. Simply K times epsilon naught A upon D. This will be the capacitance will also become K times. If you use a dielectric of dielectric constant K in between the plates as the medium. Thank you.